Today we are going to study a new algebraic structure, namely rings. So let me start with some examples of rings. The most prototypical example of a ring is just the ring of integers. So we've already thought of integers as a group, but we can think of integers as a ring if we not only look at addition, but we also look at multiplication, which I'll denote by dot. Right? So we have addition plus multiplication. Some of the other groups that we've looked at are also rings. For example, we could take integers mod n, again addition mod n, and multiplication mod n. This is also a ring. A more interesting example of a ring is the ring of Gaussian integers, which is denoted Zi. And again we have addition and multiplication. So this is the ring of Gaussian integers. And this consists of complex numbers of the form a plus b times I, where a and b are integers. You can check that if you add two complex numbers of this form, you again get a complex number of this form, and if you multiply two complex numbers of this form, you again get a complex number of this form. So this ring of Gaussian integers also, this set of Gaussian integers also has two operations, addition and multiplication. Okay, other interesting examples, the polynomial ring. You start with any field k and you look at the ring of polynomials in k, and again addition of polynomials and multiplication of polynomials. A very different kind of example is you look at the ring MNK of n by n matrices in K, and you can do matrix addition and you can do matrix multiplication. And that's again a ring. And there are some examples which come from analysis. So you look at all continuous functions on the real numbers, from let's say real numbers to usually we take complex numbers, or you could just take real numbers to real numbers. Now when you study real analysis, you learn that the sum of two continuous functions is continuous and the product of two continuous functions is continuous. So this is a ring. And in the same vein, you can look at C infinity R, which are infinitely differentiable functions from R to R or R to C. And again, in calculus, you learn that the sum of infinitely differentiable functions is infinitely differentiable, and a product of infinitely differentiable functions is infinitely differentiable. So the theory of rings encompasses a very, very diverse and wide variety of examples, and the notion of a ring is basically abstract certain properties which arise in many different areas of mathematics, including of course algebra, but also number theory and real analysis. So finally, what is a ring? So it has an axiomatic definition. So what is a ring? So let's write down the definition. So a ring is a set R with two binary operations, which I'll call plus and dot. Okay, So it consists of a set R, a binary operation plus from R cross R to R called addition, and another binary operation dot from R cross R to R called multiplication. Okay, and these operations are required to satisfy several axioms. Okay, so the first set of axioms basically says that R comma plus is an abelian group. What this means is that this plus is an associative operation. A plus B plus C is equal to A plus B plus C for all A, B, C in R. And then there is an identity. There exists 0 in R such that A plus 0 is equal to 0 plus A, and they are both equal to A for all A in R. Then the inverse axiom: for every element A in R, there exists an inverse element, which I'll write as minus because I'm using the additive notation, such that A plus minus A is equal to 0. And lastly, this abelian condition that A plus B is equal to B plus A for all A, B in R. Okay, so that's one set of axioms about the addition. Then the next set of axioms is about multiplication. So it basically just says that R under the operation dot is a what's called a semi-group. I haven't defined a semi-group, but all it means is that this operation is associated. A, B, I'll omit the dot for notational clarity. So A dot B, the whole thing dotted with C, is the same as A dot B dot C. And now, in addition to these axioms, we will have so the first set of axioms are about addition, the second set of axioms is about multiplication. Now we'll talk about how these two are related, and that is via distributivity. So says that A into B plus C is equal to AB plus AC for all A, B, C in R, and also the other way around, B plus C into A is BA plus CA for all A, B, C in R. Remember, we never said that multiplication was commutative. A times B need not be B times A in a ring. So it's necessary to state both these distributivity laws separately. Okay, and then there's this, finally there's another axiom which is called unitality. I saved this for the last, so I could have put it with the multiplication, because often this axiom is optional. So it says that there exists an element 1 in R called the unit, such that, which serves as a multiplicative identity, so such that 1 times A is equal to A times 1 is equal to A for all A in R. So for example, we look at Jacobson's basic algebra. He doesn't assume that a ring is unital, but if you look at Michael Artin's book, then he assumes that all rings are unital. When you don't necessarily assume unital, then if you want to say that a ring specifically has a unit, you say unital ring. Okay, there are interesting examples of rings which are not unital. Okay, so simplest example is maybe just take even integers, 2 times z. So this is closed under, this has an addition, it has a multiplication, it forms a group under addition, and it forms a semi-group under multiplication and so on. But there's no multiplicative unit because 1 does not belong to z. Okay, that's but there are also important examples that come from linear algebra and analysis. So what from one example from linear algebra is that you take let P be an infinite dimensional vector space, and you take the ring R equals linear maps from V to V with finite dimensional image. Then you can check that this R is satisfies all the axioms for a ring except unitality, because the identity map from V to V will have image V, which will not be finite dimensional. And another very interesting example from analysis is see continuous functions with compact support on R. Because in the ring of continuous functions on R, the unit is the constant function 1. If you multiply any function with the constant function 1, then you get that function back. But the constant function 1 does not have compact support. Okay, in this course we'll be mostly considering unital rings, but I just want you to be aware that this last axiom of unitality is optional. Okay, so let's just review. So a ring is a set with two binary operations, addition and multiplication. Okay, and under addition this set forms an abelian group, under multiplication it forms a semi-group, and these two operations are compatible in the sense that distributivity holds. And then we add this other condition that there is a multiplicative unit, so unitality. And you can see very easily that all these examples on the first page are actually rings, and in fact these are all unital rings. Let me give you one nice example of a ring which comes from group theory. So let G be a group any group you like, and I will define a ring associated to the group Okay, we'll also fix a field k. If you want, you can take k to be real numbers, rational numbers, complex numbers, whatever you like. And then we define kg to be the vector space, k vector space with basis 1g, g belongs to g. So this is just a symbol corresponding to each element of the group. So and multiplication is defined by setting 1g times 1h to be 1gh and then extending bilinearly. What I mean by extending bilinearly is that this is defined on basis vectors and then you extend it to a bilinear function from kg cross kg to g. So a general element of kg is of the form ag1g sum g in g, where ag belongs to k. Now if you have two such elements, then when I say bilinear extension, I mean you just multiply these things and take the scalars out. So you get summation g1, g2 belongs to g, ag1, bg2, 1g1, 1g2. But this 1g1, 1g2 is defined to be 1g1 times g2. And if you want to collect the terms for each basis vector, then this will become sum over g belongs to g and then sum over g1, g2 in g such that g1 times g2 is g, ag1, bg2. This is the coefficient of 1g. This is called the group ring of G. Okay, rings come in different flavors. So there are, we've already seen unital and non-unital rings, and as I said, we'll be mostly looking at unital rings. There are commutative and non-commutative rings. So a commutative ring is a ring where multiplication is commutative. So AB is equal to BA for all A, B in R. So most of the examples we looked at earlier, Z, Z mod, NZ, KX, that is the ring of polynomials, continuous functions on the real numbers, infinitely differentiable functions on the real numbers, Gaussian integers. These are all commutative. Okay, but M and R or over any field K, n by n matrices over K when n greater than 2, and Kg, the group algebra where G is not an abelian group. These are non-commutative rings. Okay, and these are somehow sometimes two very different worlds. There are people who work only in commutative rings, and then there are people whose main interests lie in phenomena which occur with non-commutative rings. Another interesting type of ring is what is called an integral domain. So this name perhaps comes from the fact that it looks a lot like the integers. In an integral domain, if two elements multiply to 0, then one of them must be 0. Then A equals 0 or B equals 0. In other words, if you take two non-zero elements, their product will always be non-zero. Okay, so here we have a catalog of examples. Which of these are integral domains? So integers are integral domains. If you multiply two non-zero integers, you always get a non-zero integer. But here's an example of a non-integral domain. Z mod 6z is not an integral domain. Why? Because 3 is not equal to 0 in Z mod 6z, 2 is not equal to 0, but 3 into 2 is equal to 6, which is congruent to 0 in Z mod 6z. So 3 and 2 are non-zero elements whose product is 0 in Z mod 6z. Okay, continuous functions. Is this an integral domain? So well, if you're familiar with calculus, then you can see that continuous functions in R and C infinity functions in R are not integral domains. You can find functions with disjoint supports, and when you multiply them, you get the zero function. However, you can show that Gaussian integers form an integral domain. Matrices, so M2k and of course mnk for any k n greater than or equal to is not an integral domain. I'll give you a simple example. You have the matrix 1 0 0 0 0 0 0 1. If you multiply them, you get 0 0 0 0. So M2k is not an integral domain. Well, I'll leave you with one more question. What about the group algebra? Is this always an integral domain?